Okay, here goes. Let's go ahead and identify some tables. Well, let's see. It looks like we have kitchen table, dining table, maybe an entryway table. Ha ha ha, not those kind of tables, right? All right, what kind of tables? Well, we're going to be looking at tables like this, our input-output tables. And we want to be able to look at a table and identify whether it represents a linear function, a quadratic function, an absolute value function, or an exponential function. I wrote some steps for how to do it. And before we go, I see step 1 says do the hoops. So I want to remind us about when we used to do the hoops. Let's say we saw a table like this. All right, let's say we saw something like this, and we wanted to know the slope. We always did the hoops to find the slope. Remember, we'd say 16 minus 12 is 4, 12 minus 4 is 8, and then we would do it on this side, 4 minus 3 is 1, and 3 minus 1 is 2. And then we would remember that slope is rise over run, the change in y's position over the change in x's position. So we would say the slope is 4 over 1, and we can also represent it as 8 over 2. But that's the same thing, right? 8 over 2 and 4 over 1 means the same thing, that the slope is 4. So remember doing the hoops to find the slope? Well, we're going to do the hoops this time, but not to find the slope. We're going to do the hoops to recognize a pattern that is hidden within our output. So let's go back to our steps. Step 1 says do the hoops, which means when I look at our first example that's on our paper, we need to do the hoops, but we are not going to do the hoops to the input part of our table. We're just going to do the hoops to the output part of our table. I'll tell you why in a second. So we're going to look at the output. We're going to say negative 3 minus a negative 1. Well, that's the same as negative 3 plus 1, right? That's negative 2. Negative 1 minus 1 is negative 2. 1 minus 3 is negative 2. And 3 minus 5 is negative 2. Now, if this question said, please find the slope that this table represents, we would do the hoops on the x side. And what would we find? Let's do it real quick, and I'm going to erase it. 4 minus 3 is 1. 3 minus 2 is 1. 1, 1. And so the input hoops wouldn't really matter because it would be negative 2 over 1, negative 2 over 1. So the tables that we're looking at in this activity of trying to identify which function a table represents, all of the inputs either increase by 1, like this input side does, or they decrease by 1, and we don't need to worry about them. They are not important in picking up the pattern that lies within the output column. So I just want you to understand why we're only doing hoops to the output side. All right, so we did the hoops and we got negative 2. What does that mean? Well, it means that if we do the hoops and we have all the numbers the same, then we stop and we identify right away it's linear. And that makes sense, right? Something that's decreasing by 2 each time, that's a constant rate of change, and we know that's linear. But what if we see a table that's not linear? What if we see something like this? Once again, we're going to ignore the input column because that increases by 1. We can ignore it. So we're just going to do the hoops for the output side. 3 minus 2 is 1. 2 minus 1 is 1. 1 minus 2 is negative 1. Wait a minute. I thought we had something linear going on here. But apparently, as we continue to do the hoops, 2 minus 3 is also negative 1. It looks linear, but not quite. We've got some 2 ones that are positive and then 2 ones that are negative. So what does that mean? We're going to go back to our list, and it says when you do the hoops, and they're the same, right? We've got linear. When you do the hoops, and they're the same except for not the same sign, so that's what we have. We have a positive 1, and then a negative 1, negative 1. Then we stop because we are dealing with an absolute value. So we recognize this as a table that represents an absolute value function. Let's try another table. Once again, we're going to do the hoops, but just on the output side. And so 17 minus 9 is 8. 9 minus 5 is 4. 5 minus 3 is 2, and 3 minus 2 is 1. I know what you're saying, Miss Overby, you kind of skipped a table. I did. I'm looking at the table that's at the very bottom of the page next to the picture of the table. So let's look at this. I skipped it for a reason, because when we're doing the hoops, we don't see the same number. We don't see the same number but different signs. We actually see different numbers. So let's go back to our steps and see what that means. Okay, if we are doing the hoops and the numbers are not the same, but they have a multiplier, then we can stop because we're dealing with an exponent. So let's see if we have a multiplier. Let's look at our numbers that we got from the hoops. Now, multiplier means, can you think of a number when you multiply 1 by that you get 2, and when you multiply 2 by you get 4, and you multiply 4 by you get 8. I can hear you. You're saying 2. That's right. We have a multiplier. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. When your hoops have a multiplier, then your table represents an exponential function. So we did the hoops. We looked at the numbers. We saw they weren't the same, and they weren't the same but with different signs, but they had a multiplier. That indicates that it represents an exponential function. Once again, when we're able to really learn more about exponential functions, you'll understand why there is a multiplier. But right now, we just have to be resigned to just recognizing when a table is representing an exponential function. All right, let's look at one more. Let's go ahead and do the hoops. 20 minus 13 is 7. 13 minus 8 is 5. 8 minus 5 is 3. And 5 minus 4 is 1. All right, I look at this. I know it's not linear because all the numbers aren't the same after I do the hoops. I know it's not absolute values because absolute value would have the same numbers, but the signs would be different. I know it's not, oh, there's no multiplier, right? Well, 1 times 3 equals 3, but 3 times 3 doesn't equal 5, and 5 times 3 definitely doesn't equal 7. So there's no multiplier. Well, and if that's the case, we already know it's not linear, and it's not absolute value, it's not exponential. It is quadratic, but quadratic does something pretty cool. Let's see if I included this in the steps. So let's see, we already said it's not exponential, but if none of the above, then do the second hoops. I love quadratics, they're so cool. There's a reason why the second hoops are going to do what they do, and you'll learn about that in calculus. But we already know it's quadratic. Let's take the second hoops and see what happens. So let's go back here and do the second hoops. So we're doing hoops to the hoops. So 7 minus 5 is 2, 5 minus 3 is 2, and 3 minus 1 is 2. How cool is that? The second hoops are all the same, and that's what quadratics do. Okay, so that's it. There are a few things to remember, right? But you always start with the hoops, and then you recognize if the numbers are the same after you do the hoops, you have a constant rate of change. We know that. That's linear. Absolute value, it makes sense that we would have 2 different constant rate of change, right? In our instance, it was 1 and 1, and then -1 and -1. That makes sense when you look at the graph. You have 2 lines meeting up that are going in 2 different directions, right? That's what our V is. That makes sense. And then we had, when you did the hoops, and the numbers after you did the hoops had a multiplier, that would make sense that an exponential would be multiplied by the same thing. It'll make more sense once we spend more time with it down the road. And then we've got quadratic. How cool is that? You do the first hoops, it seems to be nothing special about the first hoops, but then you do the second hoops and voila, you get the same number. So that's fun. And I know that you've got some activities to do with this and some sorting and some practice, and so have fun with it. And thank you very much for joining me.